Hello students, welcome back. Previously in section 1, we successfully redefined the trigonometric ratios into trigonometric functions. Now in section 2, we're going to study their graphs. After all, what's the most important aspect of a function? Well, it's a bit arguable, but in my opinion, it's the graphs. First, let's begin with the graph of sine function. Here we go. Starting from the origin, going up and down, we have a wave pattern. Why do we have periodicity? Well, that's because the angle itself is periodic. If you wrap around the entire circle, then we're coming back precisely to the same place and same pattern. So 360 degrees later, we're going to get exactly the same result. We are using the radian measure for functions. So 360 degrees is equivalent to 2 pi, so period is 2 pi, and the same pattern repeats, another 2 pi, and so on and so forth. But as we're going up and down this wave pattern, where is that coming from? That's going to be answered from here. First, a stepping stone, a static view. So the definition of sine function on your left-hand side, and the graph of sine function on your right. The definition. Sine function is defined as sine of theta is y over r, isn't it? Vertical over radius. But in this particular case, let's begin with the unicircle. A circle centered at the origin with radius 1. So instead of r, let me replace it by 1. So sine function is just y, the vertical. Make sense? So in this case, sine value precisely matches the function value here. This vertical precisely matches that vertical here. Another thing, what is this theta? Theta is s over r, remember that? Arc length over radius. But then again, in this case, radius is 1. So theta is just s. So the angle theta is the same as this arc length, highlighted in blue. So now let's go to y theta plane. And horizontal here for the graph is theta, not x. And then vertical, that's f of theta, and that's the same as y. And then this horizontal is theta. So that's the same as this arc length, highlighted in blue. Alright, this one, unwrap it and then place horizontally, then it'll precisely match this horizontal. And then the vertical matches the function value. See all those? So sine of theta, that function value is vertical y. So those two red match. And theta is this arc length, and that's this horizontal. So blue match themselves, and red match themselves. And that's for arbitrary angle. No. That's for the arbitrary angle. And here's the animation associated to that. Okay, let's slow down a little bit. And starting from 1, 0 here on the x-axis to the right, and angle increase to pi over 2, 90 degrees, and then to pi, 180 degrees, 3 pi over 2, and then to 2 pi. Alright, and then the vertical start from 0, and increase all the way to 1, Yeah, this radius of this circle is 1. And go back down to 0. Maybe I should be doing this. Yeah, okay, alright. Increase to 1 maximum. And then decrease and pass 0. And then reach the minimum, -1. Yeah, right here, -1. And then come back to 0. And then keeps going. And consequently, we have this graph on your right. So the definition of sine function, which comes from this unit circle in the left-hand side, and the graph of sine function here in the right-hand side, they match precisely. Alright, the arc length here highlighted in blue is theta horizontal, and sine value, this red, matches the function value red. At any point, this vertical in your left-hand side and this vertical in your right-hand side precisely match. As a result, we get this kind of graph. And then the pattern goes on forever and over because of the periodicity. Now let's look at the same graph this time from -pi to +pi. We have a symmetry at the origin, and this one is essentially the same as before, except that we are starting from -1, 0 instead of 1, 0. So theta begins from -pi, increase to 0, and then go all the way up to +pi, and then pattern repeats itself due to the periodicity. Finally, some properties of sine function. Let's see. We are not going to prove any of these properties. Oh, excuse me. The first line, we have the proof of everything. Sine is -1 to +1 in between, because vertical cannot exceed the radius. And then when we have degenerate triangle, when we have line segment, that's when we have sine 0 or sine possible -1, yeah. So we already went through that, and this, and then all these, when we studied the basic angles. As for the others, well, we're going to come back and prove all those, but we're going to do those in lesson 9 in the second half of the course. For now, let's just focus upon these identities based upon this graph. So by looking at the graph, let us deduce these. First, plus or minus 2 pi will just come back to the original value. That's because of the periodicity. And then it's clearly visible in this graph. Next, plus or minus pi, in that case, just opposite sign. So positive here, and then add pi, same thing but negative there. If you add 2 pi, this will go over there. So no negatives. Or here, and then plus pi, go to negative. Plus another pi, go to positive. And then plus another pi, go to negative. You can consider those like this. Also, in left-hand side direction as well. As a result, sine of negative theta is negative of sine of theta. So if we combine periodicity of 2 pi and the special case pi, we can deduce this one as well. But on the other side, you can look at this graph and symmetric with respect to the origin. You can see that too. Now, finally, this one is a bit trickier. At the same time, in my opinion, the most important. It is particularly important in trigonometric equation. What do we mean by that? If you have sine of theta Now this probably is not the right way. Equals to some y naught, then theta is inverse sine of y naught. You can easily deduce this, right? After all, that's what arcsine function does, solving with respect to the angle here, alright? But then again, by this property, pi minus of that is also an answer. Oh, no, this is not. Arcsine of y0, okay. That's probably a better way. So, when we have sine of theta equal to something, we have inverse sine, and also pi minus of that. And where can we see this behavior? Alright, let's come back to this picture. And let me expand this picture further. Okay, and then let's go to the drawing mode. Okay, let's suppose we have something like this. So what is this? Y equals to y0, a horizontal line. And then right here we have theta naught, or this one right here. Alright? And here, pi minus of that. So, within the principal domain, from 0 to pi over 2, there's supposed to be two crossings. One easily coming from the arcsine, and then the other pi minus of that. As a matter of fact, I just misspoke. From the principal domain, negative pi to positive pi. Excuse me. I marked in incorrect places. From negative pi to positive pi, as a matter of fact, I misspoke. But from 0 to pi over 2 will give you the same thing because of the periodicity. And why in the world do we have this behavior? And the reason is because we have a symmetry with respect to this vertical line, namely x equals to pi over 2. The vertical line, x equals to pi over 2. Do you see the symmetry? And that's why we have the second solution like that, due to the symmetry with respect to this vertical line, x equals pi over 2. Why? Well, that's something we are going to come back and answer in lesson 9 in the second half of the course. But for now, let's focus upon the property of sine function that comes from the graph. The others are pretty much straightforward, but this one is the most tricky, the trickiest, and also the most important. Now let's get out of the drawing mode. Other than that, the others are pretty much straightforward. Let's see, plus or minus pi, we have the same, but we are changing the sign. And then plus or minus pi over 2, sine becomes cosine, cosine becomes sine, but you have to be careful about pluses and minuses. We'll come back and discuss cosine in the next video.